Mathematics for elementary teaches with activity. For the purpose of this course, we're going to be talking probability. So we're going to be seeing basic principles of probability in this first chapter here. So we have 4 chapters in this course. So let's start in the beginning here, right? So the study of probability arises naturally in a variety of situations. Games in which we flip coins, roll dice, spin spinners, or pick cards all have their element of chance. We don't know what the spinner will land on. We don't know how the dice will roll on. This element of chance adds excitement to the game and makes it easy to design class activities and problems that present probability in a way that can be fun for students to learn. But if it's always going to be all games, it's not going to be useful for anything, right? But let's see this. If probability are only used for analyzing games of chance, it would not be an important subject, right? But probability has far wider applications. In business and in finance, probability can be used to determine how best to allocate assets. In medicine, probability can be used to determine how likely is that a person actually has a certain disease, given the outcome of the test results. So as you can see, there's far better applications than just playing with games, right? So let's take, for example, this situation here. Can I have a dance? So what are the chances that she will say yes if you wanted to take a lady to dance? So in probability, we study chances process, which concern experiments or situations where we know the outcomes are possible. Which outcomes are possible, but we do not know precisely which outcomes will occur at a given time. Example, including flipping a coin and seeing if it lands on the heads or tails facing up. Spin a spinner and seeing which color the arrow lands on. And randomly picking a person out of a group and determine if the person has a certain disease. So these are all examples of that you may know what's the possible outcomes, but you don't know for certain what's going to happen, right? For example, here, what is the possible outcome? So can I have this dance? The answer could be yes or no, but you're not sure which one is going to be, right? So for a chance process, such as flipping a coin or spinning a spinner, the set of different possible individual outcomes is called the sample space. For example, the sample space for a board game spinner is the set of colors red, blue, and yellow or green, if those are all possible colors that the spinner can land on. So we often consider not only individual outcomes of a chance process but also events, which are collections of outcomes. For example, event in the case of the spinner here would be landing on the red, blue, yellow, or green. The event here is going to be she's saying yes or no. So these are collections of the outcomes. For example, spinning either red or blue is an event if they only have 2 options, right? So in the case here, we have only 2 options. She's going to say yes or no if you're asking her on a dance. So the theoretical probability of a given event is the number quantifying how likely that event is, right? So is the fraction or percentage of times that event should occur ideally. For example, the probability that a coin lands on a heads is the fraction of time that the coin should ideally land on a head when tossed many times. For example, if you toss a coin, right? So what's the ideal probability, right? So there's only 2 possible outcomes, yes or no. If the coin is not weighted, right? It's a normal coin, it's very made it round, whatever. So I'm saying that's not weighted for one side or the other. So the outcome should probably be half of the time, right? Should be 50%. So this is the ideal, right? When we study a chance process, we usually seek to develop a probability model, which means that we take assumptions about the situation. It means all outcomes are equally likely in the case of the tossing a coin, right? So the outcomes is what tails or heads. So you think of that both of them are equally likely to happen. So half of the time. And we wanted to determine a probability for each outcome in the sample space. Remember, the sample space are all the possible outcomes. So probabilities are always between 0 and 1. So 0 means 0% and 1 would mean 100%. Or equivalently, when they are given the percentages, it's going to be 0 and 100%, between 0 and 100%. A probability of 0 means that event will not occur. And a probability of 100%, it means that certainly it will occur. So if you have a coin in hand, and how do we know for sure that a coin is fair? So this is another question that we have to think about, right? So what does a coin have to be fair, right? It has to be likely to hand half of the time in the tails and half of the time in the heads. So there are statistical ways to find out if the coin is fair or not. But one very simple way that you can do it, maybe you flip the coins many times and see how close you get to 50% heads and 50% tails. Because if you get close to that, so the coin probably is a fair one, right? So if we're important the coin to be fair, for example, the coin were to be used in a state lottery, right? Then the coin would be flipped many times, perhaps thousands of times, to determine if the coin is likely to be fair. Statistical methods exist for determining the likelihood that a coin is fair, but we will not discuss those methods here. I'm just giving you the insight of there is a possibility for that. So what are the principles that underlie how we determine probabilities? So we're going to be discussing about three principles. Several key principles of probability can be used to calculate probabilities, and we will discuss and apply these principles in the rest of the section. And here are the principles. So the first one is, if two events are equally likely, then the probabilities are equal. For example, think about the tossing a coin, right? So if the heads and tails are equally likely, which it is, right? Expect 50% of each one of them, then the probabilities are equal. So 50% of heads and 50% of tails. The second principle is the probability of an event is the sum of the probabilities of distinct outcomes that compose the event. We're going to be seeing an example of all these in application of the principle, right? But I just wanted to you to understand that when you have a probability of an event, is the sum of all the outcomes is going to be composing the event. And let's see now the last principle here. If an experiment is performed many times, then the fraction of times that an event occurs is likely to be close to the event's probability. The greater the number of the times of the experiment is performed, the more likely is that the fraction of the times an event occurs is close to the event's probability. In other words, the long run relative frequency with which an event occurred approximates the event probability. So it's a lot of words here, maybe a little bit confused, but remember, for example, when you toss a coin, let's say 10 times, right? Ideally, you should have 5 heads and 5 tails, right? But it's not maybe guaranteed that's going to happen. And even probably that's not going to happen, right? Maybe you're going to get 4 tails and 6 heads, right? But the more you toss the coin, maybe 100 times, 1,000 times, the more you're going to get the ideal proximity to proximal. The more you get the ideal is be 50-50%, right? So the more you toss the coin, is more gonna get close to that ideal. This is what it means. This is the third principle here. Okay, these are the three very principles. We're gonna be using them in exercise and examples, so you're gonna understand them better. So don't worry too much about it. So how do we develop and use uniform probability models? So if the distinct possible outcomes of a chance process are all equally likely, then we call the probability model for such a process a uniform probability model. For uniform probability model, there are a simple way to describe probabilities of an event as a fractions. So let's see one example of this. So let's assume that a number cube is not weighted. It means it's not likely to favor any side, right? Against the other. So all the sides have the same chance to face up, right? When you roll the dice. so that each side is equally likely to land face up. So this is the principle number one, okay? If two events are equally likely, then the probabilities are equal. So let's put this in a form of equation. So if let P the probability of a row on n. So n will be the numbers that you have on the faces, right? So we have a number 1, 2, 3, 4, 5, 6. And P is the probability of each one of them gonna be facing up, like here in the number 3. So it stands for the probability of rolling an n then. So we're gonna be using this equation. So the probability to roll number 1 is equal to probability to roll number 2, which is equal to probability to roll number 3, which is equal to probability number 4, 5, and 6. So they're all equal. None of them is better than the other or higher than the other, right? So the probability of either rolling 1 or 2 or 3, 4, 5, or 6 is 1. So I meant is if you sum up all their probabilities, it's going to be 1, okay? So because some face has to land up, and you can roll two numbers at the same time, therefore by principle number 2, the probability of an event is the sum of the probabilities of all distinct outcomes. So if you sum all of those 6 faces, like 1, 2, 3, 4, 5, 6, all of them together, the probability of that happening is 1. So one face has to come up, right? So has to land up. So you can use this equation. So the probability of 1 plus the probability of 2 plus the probability of 3, 4, 5, and 6, if you add all them together, it's going to be 100%, because one face is going to come up, right? Facing up anyway. So each one, you probably don't know which one is going to be, right? But one of them is going to be facing up. So the sum of all the probabilities is going to be 100%. So this is a little bit wrong, right? The probability of rolling either, no, this is okay, yeah? So it's going to be one of them, right? Either 1 or 2, 3, 4, 5, or 6 is going to be 1, right? So one of them is going to show up. So because all these probabilities are equal and add up to 1, each probability must be 1 divided by 6, because we have 6 options, right? So the probability of 1 is going to be 1 divided by 6. Probability 2 is also going to be 1 divided by 6. And all of them is going to be 1 divided by 6. So 1 divided by the number of possible outcomes. So possible outcomes is 6, right? Because you have 6 possibilities, right? So 1, 2, 3, 4, 5, and 6. And just one of them is going to come up, right? So importantly, this is very important. This applies only to uniform probability models where all outcomes are equally likely. So if any of these faces here of the dice is going to have a higher probability, you cannot use this model here. So what is the probability of rolling an odd number with the number cube? Since the outcome in this case will be 1, 3, and 5, our distinct principle choose applies here. Therefore, the probability of rolling odd number is 1, 6 plus 1, 6 plus 1, 6. So it's going to be 1, 6 for 1, 3, and 5. So it's going to be 3 possibilities for the possibility of 6 outcomes, right? So it's going to be half, right? So probability of the event, number of outcomes in the event. So the number is 3, right? 1, 3, and 5. So 3 probabilities. And the outcomes is 1, 2, 3, 4, 5, 6. So it's going to be 6 here. So again, important, this is applied only to uniform probability models where all outcomes are equally likely to happen. So this is the end of the first part of the theory. We're going to do some activities that's going to apply this theory that we just saw it. So it's going to consolidate in your mind how these principles apply. So I'll see you in the next section.